So we've got an antiderivative here of x squared over square root of 1 minus 9x squared. This is going to be a trig substitution. Specifically, we're going to let x equal, we need to get rid of that 9, so we're actually going to let it be 1/3 sine of theta. So when we square it, we get 9 times 1/9. And dx is going to be 1/3 cosine theta d theta. Now, everybody always forgets to substitute in the dx, so make sure you do that. And when we substitute these in, we're going to have 1/3 sine of theta squared over square root of 1 minus 9 times 1/3 sine of theta squared, and then our dx is going to go here, 1/3 cosine of theta d theta. Alright, now let's work in terms of theta. We need to do some simplifying. Some of this will simplify nice, some of it we might have to work with. We'll have a 1/3 squared and a 1/3, so that's 1/3 cubed, or 1/27. I'm going to take that right out of the integral. And so on top, right now what we have is a sine squared theta, cosine theta d theta. So we'll just write that all in the numerator just to clean it up a bit. On bottom here, we're going to have something nice happen. So 1 minus 9 times 1/9 sine squared theta. And those 9's cancel. So that worked out really well for us. And now we have just the 1 minus sine squared. So on top, we haven't done anything yet. And on bottom now, what's going to happen? The 1 minus sine squared is exactly equal to cosine squared. Square rooting that just gives us cosine of theta. So let's write it this way. This is just cosine theta. That's going to cancel out with this guy. So really now what we're looking at is the antiderivative of sine squared theta. In previous videos I mentioned you can do that straight from a table of integrals, but if you don't have that available, you use a trig identity. Specifically, sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta d theta. Now I'm going to pull the half out front, so 1 over 54. Antiderivative of 1 is theta. The antiderivative of cosine of 2 theta, well, that's going to be sine of 2 theta over 2 because of this 2 in front, plus c. Now we've done a nice job, but we do not have the final antiderivative. Now we're going to need to do some substituting, and we're going to use this original thing here. We know that sine of theta equals 3x, multiply both sides by 3, and therefore theta equals arcsine of 3x. So that takes care of this piece. The sine of 2 theta is going to take a little bit more work because we're going to have to actually put that in terms of sine of theta and also cosine of theta. So let's go to a new sheet of paper and we'll be able to write more of this together. So we have the 1/54th. We know that theta is eventually going to be arcsine of 3x. I'm going to put the 1/2 out front for simplicity. Sine of 2 theta, and we're going to use another trig identity. Sine of 2 theta is 2 sine theta cosine theta. Let me put that in parentheses. That is a trig identity for sine of 2 theta plus c. I don't expect you to have all these trig identities memorized, but for the exam you'd be given a sheet of trig identities. Okay, so I'm going to come up here to what we have and what we need. We have sine of theta, it's 3x. We have theta, it's arcsine of 3x. We don't have cosine of theta. So we're going to take this part and find what cosine of theta is. The way that I've always liked doing it is making a right triangle, calling, say, this angle theta. And if sine of theta is 3x, that means the opposite is 3x, the hypotenuse is 1. And using the Pythagorean theorem, that makes this side 1 minus 9x squared. Well, that should look familiar. Look at our original. So now I can find cosine of theta because it's adjacent over hypotenuse. It's square root of 1 minus 9x squared. And now let's put this all together in terms of x. So I have 1/54th arcsine of 3x minus, those will cancel. Sine of theta, as we said, is equal to 3x. And cosine of theta is square root of 1 minus 9x squared. And then we have our plus c. There's really not much more simplifying we could do. We could distribute this and maybe cancel a little bit, but I'm just going to leave it as is. And there is our antiderivative.